Hello and welcome to Business Analytics. In this introductory course, we will go over a new test called chi-square. And my name is Hari Rajagopalan, and I will be covering this material with you. So we are in descriptive analytics, and in some ways we have already moved to some part of predictive analytics. And as you can see now, this is not clear distinctions between descriptive and predictive analytics. There is some overlap here, and we are in that overlap. So if you look at the predictive part of chi-square, normally we talked about when we did the hypothesis testing, we said our independent variable predicts our dependent variable. And if your independent variable was categorical and your dependent variable was continuous, you used with two categories, you use t-tests, more than two categories, you use analysis of variance, right? So, but in chi-square test of independence, we get a situation where both our independent and dependent variable are both categorical, right? So chi-square test of independence determines whether there is a statistically significant relationship between these two categorical variables. Do the values of one categorical variable depend upon the values of another categorical variable? So let's take this example, and I hope all of you have seen red shirts in Star Trek, and we all know that red shirts are going to die. So the theory is that red shirts have a high probability of dying. If you're in Star Trek, the first Star Trek episode, and you have a red shirt, you have a high probability of dying. So here the hypothesis is that there is a relationship between the categorical variables, and in this case, one categorical variable is the color of your shirt, and the other categorical variable whether you live or die, right? So the null hypothesis is there is no relationship. If you know the value of one, it does not help predict the value of other. And what we do is we compare the distributions that you're observing to the distributions you expect if there is no relationship with the categorical variable. So expected distribution, and we'll talk about expected values a lot, expected distribution is what we get if null hypothesis is true. Now, if the observed distribution is sufficiently different from expected, you can reject the null hypothesis. So let's go about with this example. And somebody, if you look at Star Trek, there are three uniforms, colored uniforms, blue, gold, and red. And the theory was red shirts get to die on the show. Now let's look at some data. Now, this is quote unquote real data, right? People who have far more time than I have watched this closely, followed all the episodes, and have actually counted number of crew members in each one. Blue stands for science and medical. Gold was for command and helm. Red was operations, engineering, security, and this was the total crew number. And here are the fatalities, right? So the hypothesis is color of the uniform and chances of survival are not independent of each other. So remember here the hypothesis has a not. It's not independent of each other. Whereas the null hypothesis saying, well, there is no connection between the two. They are independent of each other. And so the type 1 error, we conclude that color of uniform and chances of survival are not independent of each other when they are. And type 2 errors, we conclude that they are independent of each other when they are not. So let's see how we are going to conduct the chi-square test of independence for this problem. So first thing to do is to rearrange the data set. You have to rearrange the data set such that you have one variable as your rows, which is in this case we're using color as our rows, and the other variable, which has two categories, as your columns. So we are using dead and alive as our columns too. And so we put the numbers in based on what we have in the previous data set, and we have rearranged the observed data in Excel. And the next step is we are going to calculate the expected data using the following formula. We are going to take row total, which is in the first one is 40, row total is 136 for blue, multiplied by column total, which is 40, and divided by the grand total, which is 430, which gives us 12.5. Similarly, for blue alive, we're going to take 390 multiplied by 136 divided by 430, give us 123.35, and so on. So for each one of these cells, here's the observed value. You're going to get a table which has the expected value. So here we go. We have the observed value, as you can see. We have the expected value, as you can see. And you can kind of compare the two. So here we go. Uniform. We have status of dead or alive, right? And here's what is observed. Here's what is expected. 7 here. And then expected is 12.5. Same thing for alive. You observe 129 being alive. Expected is 123. Similarly for gold. Similarly for red, right? And you will notice that the chi-square calculations is observed minus expected whole squared. We are squaring it to remove the plus minus signs, and then we're dividing it by the expected value. So it's the ratio of squared difference between the observed and expected by what from what is expected. So if you look at this, we can actually sit and look at what the chi-square value is. So we add up 2.25, and so the total for blue is 2.78, total for gold is 3.25, and total for red is only 0.15. So this chi-square value is 6.19. Take a look at this again. The real contribution to the chi-square value comes from blue and gold, whereas there is very little difference between the people and what is expected. Red people die. People who wear red shirts die or stay alive around the same level as what is expected, whereas for gold, you can see gold essentially seem to die at a much larger rate than expected, whereas blue people wearing blue shirts tend to actually die at a less rate than expected. So it is blue and gold which are contributing to this chi-square value. So the 6.19, what does it tell you? It doesn't tell you anything except that it's a large value. The chi-square value is large, and we need to really find the p-value for this before we can tell whether this is statistically significant or not. So we can get this p-value by using this chi-sq.test, and then you select the observed data, that is the center here. You select this whole thing, comma, the expected data, which is this, which gives you 4.53%, which is very close to our alpha of 5%, but it's less. So we can reject the null hypothesis and say color of the shirt is not independent to chances of survival. Now, it does not tell us red shirts are more likely to die, and you can kind of say initially, if you look at it, you say, hey, 24 out of the 40 people who died are red shirts, so 60% of red shirts died. Well, they just happen to be a larger chunk of the crew. So if you actually take a closer look, even though 60% of the dead are red shirts, the question is not if you're dead, you're more likely to have a red shirt. If the question is if you die, what color shirt are you more likely to have, right? So it's a different condition altogether. You're conditioning on your color of your shirt, and you're looking at your chances of dying, not whether if you're dead, what are the probability of your shirt being a certain color, right? So we've got to focus on the other side. So let's take a closer look. You look at this. 7 out of 136 is 5.15. 9 out of 55 for gold is 16.36. And 24 out of 239 is about 10.04. So you expect about 9.3% of the people to die, given that 40 out of 430 is about 9.3. But if you look at red, is very close to the probability in the observed probability of a red person dying is only 10.04, which is very close. However, gold is at about 16 when it should be 9.3%. So gold has a higher chance of dying, right? If you look at this, here is the graph. And blue actually has been dying at a much smaller rate. So percentage of dead, compare observed with expected, and you can see the difference. So real death rate versus expected death rate, blue shirts less than expected, gold shirts more than expected, and red shirts are pretty as much as we expected. So let's stop here, quickly move on to Excel. I'm going to show you the problem in Excel and then show you how we can calculate it in Excel, and then we'll come back to PowerPoint. All right, so here's the problem, and here's the data which was given to you. And you saw that how I took the data and made it into a cross tab, right? Cross tab, as you can see here. And we have created this information which is right here. So the expected value for us to calculate it, I want you to focus up here. You'll notice that I have used B, which is essentially your column total, B14, and you'll notice that the the B14 is your column total, which is right here, which is blue, and you'll notice that I have put a $sign on 14, so when I copy this, the row number will not change. Similarly, for D11, I have put a $, before D, so that when I copy to the right, the D column will not change, but when I copy it down, 11 will become 12. So once you set, and then your D14, which is your grand total, I put a $, on both sides. So when you copy this now, you will notice that it changes appropriately. You just have to do one formula, and then automatically everything else changes. So here is the expected value, and here is the observed value. And you can use your chi-test, and you'll notice that I have not selected the total here. So chi-square.test, you select your observed value, you select your expected value, and you can reject your null hypothesis. So here is your chi-square calculation. You can see that I am calculating each value, and then here is the total chi-square, and you can see what is contributing to this chi-square value. The larger the value, the less the p-value is going to be. All right, so we conclude that they're not independent of each other, and then you can start looking at which contributes more. So you can look at the observed values, as you see, as a percentage of what percentage of blue of the total actually end up dying. So that's about 5.15. Similarly, gold, what percentage of gold and what percentage of red. The fallacy that red people are more likely to die is because you are actually looking at the number of dead people and seeing how many have red shirts, and that will give you 60%. But that's not what you want to look at. You want to look at among the blue shirts, how many of them die? Among the gold shirts, how many of them die? And you'll notice here is your observed value. And this is what is expected if shirts don't matter, right? So it's 9.3%. And you'll notice red shirts are dying at about the same rate. Blue shirts are less likely to die. And gold shirts are actually the ones more likely to die. So this is essentially how you set it up in Excel. Let's go back to PowerPoint. Okay, now back to PowerPoint. Let's talk a little bit about, so let's look at a bonus question for this particular problem. So you know that red shirts essentially occupy 3 different jobs: security, engineering, and operations. And you could speculate that it might be security who are the ones who tend to die. And so let's look at this in greater detail. Now, we have not covered statistical tests for 2 proportions. because Excel doesn't really handle it very well. You'd have to get into very complicated formulas in Excel. And I've decided that for this particular session of the introduction to business analytics, we will not go over that. So if you look at it, among the people who are dead, security, they had over 90 people in security, 18 of them who died, and people who are not security was about 6 out of 149. So it's actually 20% of security members end up dying. So you could now say that, yeah, it is, if you're not a red shirt, but if you're in security, you have more than twice the expected chance of dying. Because remember, 9.3% was expected on Star Trek. So important to understand, if you're chi-square and you add up all those values, if it is 0, that represents the null hypothesis. If observed frequencies are the same as expected frequency exactly, then chi-square value will be 0. And 0 indicates your sample data exactly matches what you'd expect if your null hypothesis is true. Also understand that chi-square tests are one-tailed, not two-tailed, and therefore you always compare them with alpha. And you calculate it by the following steps, as we talked about. Observed, you take the observed minus the expected for each value, you square that difference, and you divide that squared value with the expected value, and you add it all up. What does this mean? Chi-square value does not mean anything unless you can get the probability or p-value for it. But it does tell you which category contributes to the chi-square. So a low chi-square contribution means that expected and observed are almost the same, and a high chi-square means that there is a wide difference. A low p-value indicates that our sample data is unlikely when the null hypothesis is true. So chi-square.test gets you the p-value, and p-value less than alpha, you reject the null hypothesis. Now, when you do a chi-square test, you have certain assumptions that you should not violate. Data in the cells should be frequency or counts of cases rather than percentages or other transformations. So you actually have to count how many things fall into this category and that category, right? The levels or categories of variables should be mutually exclusive, right? That is, a particular subject fits into one and only one level of each of the variable. Each subject may contribute data to one and only one cell in the chi-square. If, for example, the same subject is tested over time, such that the comparisons of the same subject at time 1, time 2, time 3, etc., then chi-square cannot be used. Study groups must be independent. That means a different test must be used if the groups are related. For example, a different test must be used if the researcher's data consists of paired samples. Remember, like matched samples. So you can't do that for chi-square. There are two variables. Both are measured at categories, usually at a nominal level. However, you could have data in ordinal. Remember the difference between nominal and ordinal. Ordinal data has rank, where 2 may be greater than 1, 3 is greater than 2, but it's really essentially still categorical. Now, interval and ratio data that have been collapsed into ordinal categories may be used. So let's say if you use grades and you put them as A, B, C, and these are actually categorized now, you can use them. While chi-square has no rules about limiting the number of cells, basically by limiting the number of categories, a very large number of cells will make it difficult to meet the next assumption and interpret the meaning. So, the value in a cell expected should be more 5 or more in at least 80% of the cell, and no cell should have an expected of less than 1. What I would suggest is to make sure that you have enough frequencies in each cell. When the number or the frequency counts in your cells start going much smaller than 5, it violates
chi-square becomes difficult. So try to keep, and that's why you should limit the number of categories you have so you can start grouping things together. Okay. With this, we finish chi-square test of independence, and the next lecture will be on goodness of fit using chi-square values.